We are live. We are live. Yeah, so let's give it a couple of minutes for a few people to come on, and then we go on with this thing. Yeah. So I think, if I recall correctly, yesterday we did some explorations on the FPGA code that we looked at. We basically looked at this this code that comes with the Upduino. This code that comes with the Upduino FPGA development board, and we kind of broke it down, and we looked at all the various parts and how they work and why they were being used the way they were being used. And I think to that end we got a little bit comfortable with that code. And I think today the thing I'm gonna do is I'm going to are we live? Are we live? We are live? We are live? Live, maybe? Yeah. Okay, cool. So what we're going to do today is basically go through this code, and then I really did consider like going from scratch completely again, but I thought the best thing to do is to just go from code I know, code I already understand, and then build it up into becoming a CPU. So what we're going to do is going to modify our RGB LED driver that's on the FPGA right now. So this code over here, the code that I'm breaking down over here and this blog, we're going to modify this code, and rather than actually driving the RGBs directly from the counter and just looking at bits in the counter, we're going to actually implement a tiny, very, very, very tiny, something like a 8-bit CPU that will enable us to see how a CPU works and start getting comfortable with how these things work. And I did do some notes on this, and they should be in the description of the video, but this is it. But really the things that we're going to add today are going to be very small. As always, understanding the thing is rather like, it's harder than actually doing it. The code that we're probably going to write something like maybe 20 lines of code. That's really what we're going to add. And this being like 50 lines of code, we're removing some, and we'll add maybe another 20, and it will end up at something like 60 or something. So really the new code that we'll write today that hasn't been covered in the other stream is going to be something like 20 lines. So first of all, let's put this somewhere and run it and see that it actually does do the thing it's supposed to do. And then after that we can start like kind of modifying it into a CPU. So I'm in documents, so cd hdl, and then in here we can do tiny CPU. I think so. And then in a cd tiny CPU, in here we can do something like, there's a few things I can do. I can do something like up here, create, I think, board, Upduino 3. Now cut up here, cut up your ini, up here.ini. Cool. Yeah, cool. Let's do that. And then what we want to do is we want to make a main.pcf. So touch. Actually, I can just copy it from somewhere else. That's in there, and then it's going to be in something like Upduino, and then it's going to be in RTL, and then it's going to be in Blink LED, and then I think it's something like main.pcf, and then I want to copy that here. Cool. So what else do we have? So now we need a main.v. Touch main.v and main.v. I'm so used to C, and then in vim, boom. And then what I'm gonna do in here, this is already enough to make our app. What I'm going to do in here is I'm just gonna copy this code this code so that you actually have access to it from the starting, but it's in several places. And what I'm going to do now is I'm going to go into my Verilog code and I'm going to put this Verilog in there. Okay. I don't like the way it's showing, but that's fine. That's okay. Let's remove the comments to make the code a little bit less shocking, so that it's actually the size it's supposed to be. But if indeed you do want the comments, you can keep them. That's erroneous. And I think that should be it. And I think if I Control Shift T, if I do uphill build, we should get a build. Let's see if this actually works. That should be good. Main not found. I know why that's there. It's because this module is it's not called main. I think Upio expects the module to be called main, so I always, with other tools, you should be able to use other module names. And also, I'll see just now, main, space A, Control E, and then space PP, and then let's do Upio I9. Let's see. Yeah, top module main. So we could have named it something like, we can actually just go and change it. We can change it, and I think we can do something like tiny CPU. Cool. Actually, this is cool because I'm learning how to use Upio, and I can go Upio build, and it should fail because it goes like no module called tiny CPU, and I don't know if this is gonna give me problems, but let's see. If I call it that and I say tiny CPU. Okay, cool. And then if I build it, let's see what happens. Upio build. I don't know if it's going to work with my main. Cool, it does actually work. So here's my Upduino. Let's run the code and see what that code actually does. And I want to do iceprog. Control R, iceprog. And that's it. It should flash it, and we should probably get some links. Yeah. Something like red, blue, green, red, blue, green, red, blue, green. So this is the code that we went through yesterday. This is the exact same code that we went through yesterday. But what this code does is it goes through a counter, and then it checks two values in a counter, and whether those two values are set or unset, it actually blinks an LED. We covered this in the previous stream, so if you're looking for it, it's in a previous stream. It's something called like FPGA LED blink teardown or something like that, but it's going to be in one of the things. So what are we going to do today to this code to make it a CPU? We're going to make it a CPU. So what the things that we're going to do, I write notes when I study for this thing, so there's a detailed thing in my notes. And the thing the main changes that we're going to add is we're going to add a CPU register, some sort of like general purpose register that we can use to store what needs to be run or what instruction we need to fetch. Okay, and then we're going to add a program counter, and this is just a pointer to the instruction that we're running right now. Our CPU is only going to have like 3 instructions. It's going to be something like I think increment, output, and then something like no operation. So do nothing. It's a very very tiny CPU. We're not trying to build like a whole. Eventually, we will try and maintain. We will try and implement a RISC-V. I'm thinking a RISC-V, either I, maybe we might even do an M. But so RISC-V CPUs, RISC-V CPU. RISC-V CPUs come in like various levels. There's various levels. So there's one, you can make them like very inefficient, and then you can go all the way. So these are all extensions. They're like multiplication, atomics, floating, double precision, floating, and there's all of these things that you can add. But I think what I'm going to try and do is I'm going to try and do the basic one. Like I think there's an I one, there's a RISC 5i, which is the beginning one, the one you start with. I'm going to try and implement that one, and then once I've implemented that one, I'm probably going to find like a production RISC 5 CPU that's implemented, and I'm going to keep working on that rather than trying to reinvent the wheel myself. Because I'm doing this in order to learn how to do fast data paths. So I want to move data quickly, especially say between like MIPI and USB and things of the sort. So the point isn't to build everything myself. The point is to learn how these things are built and have the proper concepts in my head so that I can walk into a code base that exists and do something with it. Cool. Yeah, so that's really what we're going to be adding to that code today. And then after we add those things, we're going to add a slower clock so that we can actually use the rising edge of a very slow clock that we use to kind of build up stuff. So I think an easy way is to just start. I usually go through this, but an easy way is to just start writing the code. Before I do that, I'm going to check on questions and then I'll jump straight into the code. Thank you, Bartholomew. I didn't know that. I will try and adjust. Let me actually do it now. I'll do it now. Sorry. Thank you for letting me know that the audio is quite low. Yeah. Bartholomew, can you please check? Can you hear me better now? And I'll try and even speak louder. Or is this too loud? Please let me know. Please let me know if you can hear me, or if you can hear me better. Then I'll start the code. So that's basically what we're going to be doing today. We're going to go from this code that we already understand how it works, and then build up, add some features to it, and then it will become a CPU, and boom, we have a CPU basically. Let me check. Can Bartholomew hear me? Bartholomew. I don't know. That's how we say it in English. I don't know if that's how you say it in Polish. But for sure. Okay. While Bartholomew decides whether they can hear me or not, we will keep going. So let's actually just jump into this code and start doing it, because this is quite, it's like I said, it's simpler than it feels. Cool. So here we go. So we have our outputs already defined. We are going to leave them. We have so this is our let's label that so that it's easy to know. This is our clock connection. Okay, cool. And then that's our counter. This is actually, can I label them? No, I don't like doing that. Clock connection, counter, and clock setup. Okay, so these three. We have the clock output, basically clock output. Let's label it like that. Clock output, counter register, clock output, counter register, and clock setup. That's what those three lines do. So the next thing we need to add is a bunch of let's add the three things that we talked about before. We talked about adding a CPU register, a program counter, and some ROM memory. Okay, so let's start that. So we can have because we're making an 8-bit CPU. Because we're making an 8-bit CPU, I think we can do like 8-bit instructions. Like an 8-bit instruction where the lower 4 bits are what the data, and the upper 4 bits are the instruction. So 4 bits. Okay. So what do we need a CPU register for? We need a CPU register to store what is the data that we're holding in right now. What is the data that this thing is doing? This thing is holding data that says which pin is on or all pins are off. So we need 3 bits. We need 3 bits for So registers. So let's do CPU general purpose register. So this we can label it something like reg, and then this will be 20, yeah. So that's 3-bit general purpose register. Let's call this A. Okay. And then let's make a program counter. A program counter that accepts. Our program counter should be able to hold a 4-bit instruction. So the program counter holds the address of the next, or rather, the program counter holds the address of the currently being executed instruction. Okay, so let's make it a 4-bit program counter. So 4 bits, 4-bit program counter. So reg, I think it's 3 and 0, and then in here let's label this a PC. Okay, perfect. And then after that, what did we say we need? We needed some ROM memory. So we need some ROM memory, and I think I'll add something like, let's add something like, we can add something like 4 instructions, but let's add like 16, I guess. 16 8-bit instructions. So some ROM memory to some read-only memory. Usually what you do with this read-only memory is you store your program in it, your code in this. But the moment you start introducing the concept of code, you basically need to introduce the concept of a compiler and a way of adding the code to the CPU. That's not kind of what I want to do. I want to do something really simple. So rather than actually having code, what we're going to do is actually just hold a few instructions, a few statically defined instructions. So let's keep this like as simple as possible, as bare bones as possible, so that we see if we can understand it and how it works. So let's add something like 16 instructions in our read-only memory. So let's add some read-only memory, ROM memory. I think each ROM memory is going to be 770, and then in here we will have an array of these, and this array is going to have it's going to be called ROM, and it's going to be 16 long. So it's going to be 16 long. When you're defining these ones, you just start, you do it opposite. So it's 0 to 15. When you're doing arrays like this, you do 0 to 15. And remember, we have that cheat sheet. So we do have this cheat sheet. We have this cheat sheet from Stanford. Where is it? There's a cheat sheet somewhere in here. Is it in here? Yeah, there's a quick reference, and I think we want to look for, oh no, that's the wrong part. We want to look for, sorry, I need to make it max. So we want to look for Control F, array. Yeah, so something like here. So what we're doing here, this is, oh yeah, but that's not the way we want it. We want an array of something that is longer than 1. So where can we find array? Can we do array? It's only 1. Okay, cool. I will leave this for now, but you can Google it and you can find it. Yeah, so you can have an array of integer values, and this one goes from the small one to the long one. But when you're defining the register itself, it's 0 to the least to the most. So this combined with this, so we have 16 registers whose size is 8 bits. Is basically what we've done here. 16 registers whose size is 8 bits. Okay, so that's even 16 registers whose whose size is 8 bits. I think I can, yeah, let's save that, and then perhaps I can even pose for like a question or two so that I can even catch up to myself. Let me see questions. Any questions? Yeah, it's okay now. Perfect. My audio is good. Thank you, Bartholomew. Okay. Let's do the next thing. So we've now let me go back to my reading list. We've defined a CPU register to store both data and addresses in our case, and then we've defined our program counter that just holds 8-bit instructions and data. So there's going to be instruction and data in there, but actually we don't even need data because right now we just have instructions, so we don't need data to do anything with it, and everything is almost static, so it's fine. We have ROM memory, and then we need to define our slow clock. So here, after our clock is defined, so this is the so here we run the oscillator on the FPGA, or run the oscillator primitive on the FPGA. Okay, and then in here we want to, so basically divide the output. That's odd. Something is wrong. That code shouldn't look like that. Okay, run the FPGA oscillator. Anyways, when we get to it, the thing will tell us. So let's do the divide the oscillator output by 2 to the power of 25. Yeah, so that's really what this line here does. So let's add a wire. Something is wrong. Somehow I've messed up. Okay, let's see wire, slow, CLK. Somehow I have messed up, and this is going to be frequency counter, and then we only check when frequency counters, this 24th bit is set. I have messed up somewhere here. I have messed up. Let me go and see the code. So this that goes like that, that goes like that. Da 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 da. Da 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 da. If anyone notices where I've messed up, please tell me. Okay, cool. And then always positive edge, that, and can I build it? Frequency counter is implicitly declared. Frequency counter I think that's the one. Let me see, can I wait, it actually built. There's no issues. So I probably need to get my linter to look at Verilog properly. So something is wrong with the way my linter is highlighting Verilog. So I will get to fixing that somehow soon. But so we've added our slow clock here. Now once we've added this slow clock, now we need to do, let's think about what we want this to do. What I want to do is, since we have 3 LEDs, I want it to go like, when it's 0, 0, when the bits are 0, 0, 0, light no LED. when the bits are 001, light one of the LEDs. I think it's whichever one is going to be RGB 0, and then 2, and then 010 is going to light the second one, and then 100 is going to light the third one, and then something like 111, all of those things. So I think what I'm gonna do is something like initial begin. I wonder what I have messed up so much that my thing cannot even do. And let's look at the cheat sheet we have. So Control F, initial begin. So this is used to run things that run before the first clock cycle. Basically, this is like setting up the data so that we can use it later. I mean, it's like kind of setting your globals. Let's assume it's like setting your globals, yeah? So let's add initial begin, and then at the end here we're going to do end. I do not like that this doesn't do this, but let me see. If I do this, what will you do if I do this? Somehow this doesn't want to recognize. There's something here that is making my thing go crazy. Anyways, we'll find out later. I think the code will run. Does anyone see anything? I think the code will run, but let's we'll see. So here, initial begin, this should just be one step. And then here I want to do something like, let's do so we want increment, like, look, there's only one instruction, it's like output, but we want to output this, output the next one, output the next one. And so there's the two instructions is, we have a no operation instruction, which is do nothing, and then we have this other instruction that is output, basically light an LED, and then we have this other instruction that is go to the next instruction. That's how I'm thinking about it. And I think that we can even like just make them like this. So let's make it, our instructions could be something like ROM, ROM 0, okay, and then let's make the first one 001, and then 000, and then ROM 1, and then in here we can do equals 00110 000. So this is increment, basically go to next. Wait. I think I need to finish these ones, terminate these ones with this one. So go to next instruction, and then here we want to do something. This is output result of computation. And I think we can just do pairs of this all the way. Do we want to do that? Pairs of this all the way or something? No, that's fine. And then ROM 2, so equals to 0001 000. Okay. ROM 3, let's do the same thing. It's just a loop. We're running a loop. 010 000. Yeah, I don't know why this is like really disturbing that my code is doing this. Actually, that's quite fine, but that's fine. So that 001 002, and then this will light the first LED. No, the second LED. Okay, and then let's do the third LED, and then from the third LED we can kind of from the third LED we can kind of freestyle it, isn't it? Don't we do that? From the third LED we can kind of freestyle it from there. I think so. So let's do that, and yeah, I think we can even okay. So this is output. Go to next. Go to output. Go to the next output. Okay. So this is ink. Go to next. So let's actually use this one, and let's do Y, and then we will come here. SP. I don't know how many those are, but let's see. So tab. Okay, cool. So we're gonna come back and fix this. I really need to learn my Vim foo so that I can actually do this in one step, but I've not been doing that. I usually don't write code like that, so I don't have that movement in my hand that I can just do that. So we got to 2, so this is 4, 5, 6, 7, 8, 9. Do we want to flip them? Do we want to just keep flip-flopping? Yeah, I don't mind keeping flip-flopping. I do not mind keeping flip-flopping. So let's do 1, 0, 0, 0, 1, and then 1, 0. Let's just keep it simple so that we actually see this working. So 0, 0, 1, 0, and then it's 1, 0. And then the other thing we can do is, because this is 9, we can come back and copy. We need 6 more. Y, and then I can come back. And then, so let's go. Yeah, this is going to be 10, and then this is going to be 11. This is going to be 12. This is going to be 13. This is going to be 14. This is going to be 15, and then we don't need anything there from there on. Okay, I think that's it. So we've added. This is our read-only memory. This is just. It just does light this one, go to the next one, light this one, go to the next one, light this one, go to the next one. Just that's what it does. That's what happens there. Yeah, cool. So that actually fixes all of that. And then, so the thing we need to do, if you recall correctly from yesterday, this was actually the thing that was doing all the computation. So basically, we were waiting for all of this. To be set. Whenever the 25th and 24th, we were using a combination of the 25th and the 24th bit to change the LEDs. But right now, let's use our CPU. So our CPU should go like, light the first LED, point the instruction to the next one, light the second LED, point the instruction to the next one, light the third LED, and then it should just always like loop on that. So let's do an always. We know this one from yesterday, and then here we can do always at pause edge. So pause edge is rising edge, slow clock. So yesterday we used the frequency counter here, but today we're going to use the slow clock, and then we're going to do begin, and then in here this is a loop. So in this we're going to do let's read the ROM memory, read the first 4 bits of the ROM memory. Yeah, read the current register and then the first 4 bits of the ROM memory, so that we know what instruction to do now. Okay, so case, and then in here I can do it's just normal, I mean ROM, and then in here I want to read ROM PC. Remember, the PC program counter stores the address of the instruction that we are executing. So let's it makes sense. It makes sense, I think. And then we'll read from 7 all the way to 4. So that's the first 4 bits, and then we can read that. And then after we read that, we can do, this is an end, I think, here. Yeah. Let me see my notes again. This is an end. I'm so bothered by it not highlighting my code. So that's cool, but it's fine. So we have that, and then we have CPU instruction to execute them. So we fast fetch an instruction. You see, we read the higher 4 bits that encode our instructions, or 1 for increment, or 0010 for output. Then we use a case for getting our opcodes. So what we want to do is, yeah, I think in here we can do case. Let's see how cases are done. Case. Let's add that. Case. Where's the case? Yeah, so here, this is what we want to do really. That's case, state, and then based on the state we can do some stuff. Okay. Cool. So that's actually what we want to do. So case the first 4 bits of that thing. In there we can do something like 4. We want the fast binary Bob. It's 001. No, 01. So in case those bits are binary value 001, we can put in A. Remember, this is the non-blocking assignment operator. So while this is happening, something else can happen. So we'll get later when we were packing multiple instructions in a clock cycle, and it's called, I think, packing or something. We're going to be doing we will learn why this operator is so effective. Basically, it's a non-blocking operator. It lets you do more stuff. B00010. This is a do nothing one. Yeah. So here do nothing, and then we can do that, and then we can implement a default, I think, and then we need to implement a default if I'm not wrong. And then in here we can do something like, I think it's end case. Yeah. And then after we do end case, I think it's those binaries up there. Yeah, I'm pretty sure it's the binaries that are fixing out. Oh, and this reminds me, all of the other anyways, let's PC let's use the non-blocking operator again, non-blocking, and it calls PC +1. So we read the PC, we do something based on the PC, we increment the PC. Okay, and I think the problem comes from here. I found the problem. This is, I think, 8B. 8. Yeah. 8. 8 binary. 8 binary. Okay. 8 binary. No, is it that? Is that how it's done? 3 binary. Yeah. So 8 binary. 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 Somehow I'm messing up. Let me do it. Just give me a moment. Is this actually how it should be? This is me learning code live. 8 binary. 8 bit. 8 bit. And this is my 8 bits. 8 bit. 8 bit. 8 bit. 8 bit. 8 bit. Is this really how it's done? 8 bit, 4 bit, 4 bit, 8 bit. Does anyone see anything? But if that's the case, then why is it alternate highlighting like that? Why is it alternate highlighting like that? what I don't understand. I feel like I'm doing something bad in the code and it's not working. And I feel like I want it to be like this, but it could be just that I don't have a Verilog linter in my setup. So let's look at that. PC equals PC plus 1 set. That's okay. That looks sane. And then here, this is where we basically come to apply the PC output, the program counter output, RGB LED1, and then this is going to be A0 or A2. We can even go A2. And then, so we can learn how to count, from most significant to least significant. That way when we're hanging out with people who count in binary, you can count with them. A0. I think so, and I'll go back here and just bring this in because it makes much more sense if it's somewhere here. Yeah. Okay, yeah, that's fine. So let's actually do that. That way, everything. So the other thing you'll notice is that Verilog people use tabs, and they use tabs to. If you watch the Sean Heimel video on learning Verilog, you'll see that Verilog people use tabs and they use them to align stuff, and I think that makes readability easier, which makes everything work better. Okay, so let's go see if this thing gives us. By the way, that is it. That's it. That's our CPU implemented, because we have, rather than lighting the LEDs based on the counter that we had before, we're lighting the LED based on an operation we are doing in the CPU. So the CPU is actually doing some computation, and then based on the result of that computation, we're then actually lighting an LED based on that. Yeah. Let's see if it builds. I'll be very shocked if it just built. It just built. Any questions so far? Anyone with questions? Well, I think we just go straight to flashing this. I feel like it's not going to work. I really feel like it's not going to work. So this is a former program running, and let's see if we can just, it should work kind of the same, but let's see. It's now setting it up, it's running it. Yeah, you see? Oh wow, it's working. Oh wow, we built a CPU. Red, blue, yeah, some sort of mixture, green. Yeah, so there's obviously some corruption in our data because we don't get them in really good order. If you see that, there's obviously some corruption in our data, but we built an 8-bit CPU. Let's go look at our data. Why is it like that? So 0 1 1 0 0 1 1 0 0 1 1 0 0 1 1 0 0 1. Yeah, it's okay. Looks okay. Everything looks okay, but we have some corruption somehow. Because 0 1 0 1 0 1 0. TS update. Okay, so it thinks it already has a parser. Just a moment. And then let's go to the end, and then let's go to .config .nvim. I think here, let's check in here. Lua. No, I want to check my after. I want to check my plugin, and I want to check my LSP config first of all. Do I have let's add dot v, I guess. Yeah. No, this is for Clang. I don't need that for here. I don't need that. I don't need an LSP here. See? KKK. I just need somewhere where I'm defining my languages. Okay. I think it's in Trisita. I do have Verilog over here. Okay, cool. And then telescope is just fine. So this is fine. It's just there's something that is making my IDE not identify the code correctly. But really, what we just did is we implemented an 8-bit CPU on FPGA. We just did it. We made it work. So let's actually just review. All we added, I can do a, no, I can't do a get diff because then I would, this is a new one. So let's go back here. So let's go. We added a couple of CPU registers so we can store what we're working on at the moment and what it is that we intend to work on next, okay? And then we added some ROM memory to hold our instructions, the set of instructions that we're going to do for this. And then after that, we added CPU. We added so that the CPU can fetch the instruction, execute the instruction, and then increment the program counter. That's how all CPUs work. They fetch, execute, increment. Some CPUs can do all of these instructions in one clock cycle. They can do all of these three things in one clock cycle. Ours is a little dumb. It does everything. It does one thing at a time. So eventually we can make it better. I think the next time I work on this, probably during the weekend when I don't have a lot of work, I can build a more extensive RISC. Actually, RISC. This is a RISC style CPU. This is not a RISC CPU because RISC is this, but RISC CPU is just a reduced instruction set. Really, that's really what it is. So if you have, you don't have a full instruction set, you just have a reduced instruction set computer. So this, we have built that, which we have something that fetches instructions, decodes the instructions, executes the instructions, and then increments the program counter, and it goes out boom 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 all over again. And so that went smoother than expected. Yeah, so we slowed down the clock. We ran the processor on the rising edge of the slow clock so that we can actually see the LEDs blinking slowly. If we ran it on the big clock, it would work, but the LEDs would go so fast it would be permanently white, or something, or some sort of mixture of an RGBA color. Yeah, that really is it. That really is it. I think so. I don't see anything missing. This is just masking. This is, yeah, cool. Does anyone have any questions? So we can just do that. Git status. Git init. Okay. And then I'll go to GitHub. It's hard to go to GitHub on the stream because then it loads up with like notifications and stuff. Let's make a new repository. Tiny 8-bit CPU. Okay, and let's just make that. Create. And then here we're gonna do git status, git add touch.git ignore, and then here we're going to be nvim, and then we're gonna change this, and then we're gonna add build git status, git add dot git ignore dot api init git commit dash m tiny CPU create ini for board and dot git ignore okay, and then git status git add main.pcf git commit dash m tiny CPU define pins for the LED output. Okay, git add main.v git commit dash m add tiny CPU naive implementation of 8-bit CPU. That's it. We have a CPU and it's running, and that's awesome. Let's push this up. Oh. Yeah. Need to add the remote. And then git push. Git push -- set upstream origin main. I forget my git cannot complete. Okay. Okay, cool. And I will take this. This is already up. We should add a readme there. Touch read me .md and vim tiny naive 8-bit CPU Verilog implementation of a naive 8-bit CPU on our FPGA, the Upduino FPGA. Yeah. Git add readme git commit -n add tiny CPU add CPU doc git. Hey Bartholomew, which FPGA do you have? Can I ask? Which one do you have? I'm very interested in knowing whether you can just take the code I've written and you can basically put it in your FPGA. I know you, unless you have a Lattice ICE41 based one, I know it's going to be difficult to do. Xilinx, okay. I've never used that one. That's a huge one, isn't it? That's like, how many lookup tables does that have? So Bartholomew has a Xilinx Spartan. I have that one. Xilinx Spartan XC350A. How many lookup tables does that have? I think it's super big. So that has zoom so people can see. So you have the 3500E or 35A. Where is it? 350A, 350A. I don't see a 350A. Xilinx. Let me just copy it from the comments. Copy. Yeah, I feel like this one is much bigger than mine. So how many lookup tables does this have? Yo, 16 MB, USB 2.0, and then you've got yeah, you have like an seven segment display, so you can't use something of so. And you've got like serial over there. That's so cool. 39 IOs. That's huge. How many lookup tables? I don't even know how to look at FPGAs. All I look for is how many lookup tables, and then I know if you have more lookup tables than what I have. 16 MB, that's a lot. LUT. I don't know. It doesn't tell me how many you have, but this looks cool. Yours is much cooler than mine. It's much cooler than mine. My small one. Yeah. So you have 8 LEDs, user-defined LEDs. Yo, wow. You do have LEDs actually. You can, if you know how to use the LED driver on top. If you know how to use the LED driver on your, you can basically change my code to work on yours, but you can also write yours just straight on. That's cool. What kind of CPU are you implementing, Bartholomew? Are you just doing like a small toy one like mine? Or are you actually doing like a RISC-V or like something big? Or are you doing like a proper desktop CPU? You also have VGA output. That's so cool. So you can use this to drive. You can use this to drive your normal screen, your normal monitor. Yeah. Any more questions? Any more questions from anyone else? Any more questions? Any more questions? This session has gone surprisingly smooth. Like I'm trying to run. You're trying to. Oh yeah, I see. But it's going to be. It might not work. Well, the only part that wouldn't work is the silicon blue stuff. So this, I don't know if you remember from yesterday. My cats are fighting on the floor. I don't know if you remember from yesterday. So the SB, tomorrow. Zephyr, tomorrow, back to audio. I was just tired today. I was gonna do the FIR today, and then I got tired from the thing yesterday. So the SB is silicon blue, and I think silicon blue belongs to Lattice. I don't know if Xilinx has it, but if they do, then it should work. All you need to do is convert my LED driver into your LED driver, and then we can go back to it. But yes, Zephyr stream tomorrow, going back to FIR with audio. But I've been doing quite an interesting project at work. We're doing some keyword recognition, and we have to do FFT and then do an FCT, and we have to do a fast Fourier transform of the audio signal, and then we have to do a fast cosine transform, and then after that we can apply something called MFCC coefficients, and that is basically used to detect things like keywords, something like hey Google, hey Apple, hey Siri, something of the sort. But that's gonna be cool. You love FFT. Yeah. Are you looking for work? Bartholomew, are you looking for work? I also love FFT, but it's scary for me sometimes. It's hard to understand. Yeah. You can mess up easily. And then it's easier when it's discrete, when it's already a Fourier transform, I think. But when you're doing like integrations and and deviations and calculus, it's so hard, man. But it's so fun when you get something to work. It's so cool. Anyways, we're going over time. It's been an hour. We built an 8-bit CPU. It worked. It's amazing. So here's the 8-bit CPU again, blinking LEDs, as always. Thank you so much for everyone who showed up. That was really cool. Thank you for showing up and supporting me. Thank you. Special thank you for Bartholomew for showing up and writing code on his Xilinx while I'm writing code on my FPGA. And it's amazing. Thank you, everyone. See you guys later. See you tomorrow. We'll do a Zephyr stream. We'll go back to audio and we can do that. I see. That's cool. If you use it heavily in MATLAB. So are you coming from like hardware design to... Are you coming from hardware design to embedded, or are you coming from data science to embedded, or is this stuff we just use everywhere a lot? There's a lag because I say something. I read a comment and I say something, and then it takes a while before he gets it and then he replies. My internet is slow. Anyways, thank you all so much. We have the Discord. We can discuss in the Discord. Oh, and as always, I forgot to say, let me actually link the code that we did. I forgot to say. The video has a link to the Discord channel or Discord server. Please join us, talk about stuff, and we can always like, it would be cool to have more people to talk about and do stuff together with. Yeah, this is not that. Okay, cool. That's that. And then Control Z. I don't want to do I don't want to delete everything. I just want to remove that. I think I can do something like, I don't want to do that. Yeah, cool. That's easy. Invite people. Edit invite link. Never expire. Generate new link. Copy. Let's put it in the thing. Discord server. Anyways, once again, thank you so much for showing up. You are an electronics engineer, but you work as an embedded systems programmer. Man, you're lucky. You got everything. I didn't go to electronics classes, so I just went to computer science classes and math classes a bit. And as always, Yin is here. Jan is here. Jan says good night, and we'll see you guys tomorrow. Thank you so much for today. Tomorrow we work on audio again, and we go back to doing FIR filtering on our audio. Cheers. Thank you so much. Very interesting background, Bartholomew, and we should learn more. We should share a lot, and let me know. Thank you. Cheers. Cheers, everyone. Thank you. That was amazing.